Welcome to standing waves and open pipes. So open pipes are used in musical instruments, often in flutes and recorders. With all pipes open and closed, we have longer the pipe, the lower the pitch, and then the vibration is going to be at the open end. At open end. So we'll always have an antinode at the open end. Alright, so here I just have a reminder of what these waves are going to look like on a string. So N, remember that is our number of antinodes. On a string, this wave would look like this. We have got one antinode. In an open pipe, this waveform, remember, vibration or the antinodes are at the open end. So this is an open end and that's an open end. We need to have antinodes there. We need to have one antinode in total. So we're going to look like that. Here's an antinode, and here's an antinode. So that would seem like maybe there's two, but this is only half of an antinode, and that's only half of an antinode. And here in the center, we had a node. All right, so if we go to the second harmonic, n equals 2, we've now got two antinodes. We still need antinodes at the sides, so that this half and that half is going to equal 1, and now we need one in the center as well. So we're going to look something like that, with an antinode here, and an antinode in the center now, with nodes right here. For the third harmonic, got 3 antinodes. We come over to our pipe. We've still got antinodes here. So those are going to be 1. And then we're going to need 2 in the center. Something like that. With an antinode, and then nodes here. Our fourth harmonic, 4 antinodes, and then again 4 antinodes here. Now we're going to need 3 in the center, so got an antinode, another antinode, then antinode. There, those all add up to 4. Our nodes are here. Let's find our wavelengths for each of these. Is our string or our pipe length is L. Here, lambda over 2 is L, right? Half of lambda, our wavelength, which looks like that. That's the full wavelength, but there's only half of it in L, so we have that. Here would be our full wavelength. So again, we still have lambda over 2 is equal to L. Let's do that over here. We've got lambda equal L. Same thing with our string. Over here, 3/2 lambda is equal to L, right? Because 1.5 lambda is 3/2, that's 1L. Same thing here, we've got 1 full wavelength and then half a wavelength. And then here we've got 2 wavelengths is equal to 1L. Same thing here. We go from here to here, and back again. So if you look at all of these wavelengths, that's our first, second, third, and fourth, you can see they're getting shorter relative to L, right? Here, we have lambda is equal to 2L. Over here, lambda is just equal to L, so it got smaller by a half. Here, we solve this for lambda, we get lambda is equal to 2/3 L. 2/3 of L is smaller than L. And then here, if we solve this for lambda, it's equal to L over 2. So our lambdas are getting shorter. Pitch has to do with frequency. So the speed of sound is 343 meters per second. It's also equal to lambda times f. As the number of antinodes increases, lambda goes down, right? We just saw that here. But the speed of sound remains the same, which means that lambda times f needs to equal the same number. So frequency must increase. Frequency going up means higher pitch. If n goes up, lambda will go down and frequency will increase. The more antinodes you have, the higher your frequency, the higher your pitch.